Right, good evening everyone and welcome to this CIWEM Scottish Branch webinar. My name is Alice Gent, the chair of the CIWEM Scottish Branch, and I'm really pleased that so many of you have been able to join us this evening, particularly as it's such lovely weather outside, and also glad that technology enables us to gather together to continue to share knowledge as we've been doing with the past few CIWEM webinars. And this evening I'm delighted to welcome Rachel Fox, who is going to be presenting this evening. Rachel is a technical lead at Scottish Water, working on resilience and the regional strategy. She's a chartered engineer with a background in wastewater and a particular interest in resource recovery. Rachel joined Scottish Water in 2013 after completing a PhD in anaerobic wastewater treatment and has since worked on various environmental projects focused on innovation. The discussion today will focus on Scottish Water's approach to innovation in wastewater and will explain the drivers and area of focus for the current programme and how innovation will fit into SR21. Throughout the evening, there'll be an opportunity to post questions to Rachel, so please use the Q&A feature located at the bottom of the screen, and Finlay Cameron, a colleague on the CIWEM Scottish Branch, is going to read these at the end. Thank you very much, Rachel. Over to you.
Great, thanks very much, Alice. Yep, so I think Alice has already said we'll just do a bit of a whistle-stop tour through wastewater innovation and what that kind of means for us at Scottish Water this evening. If you're wondering what I look like, that's a picture of me on the screen. At least that's what I looked like before I've survived for 3 months without a haircut. So no cameras on this evening. So I'll invite you at the beginning to cast your minds forward to 2040. Imagine you've just got out of bed, gone for a shower. You probably don't think every day about where that water goes and what might happen to it, but you know, today it would go to a sewage works. Where might that go in 2040, and how might it be beneficially reused? Or perhaps you've looked out of the window and it's raining. Certainly not raining in Edinburgh this evening. It's actually a lovely sunny evening. But again, where might that water go once it's fallen out of the sky, and how might that be different to what happens to it today? And similarly, what might our toilets and our plumbing systems look like in 2040? How could we recover the resource from our wastewater? And also, what might we know about ourselves from our wastewater? What can we understand about our own health and maybe the health of our communities through the sampling and analysis of our wastewater? So keep that picture of a potential future in your heads as we go through this presentation. And let's think about the role of innovation, how we might want to innovate to get where we're going. Now, if you paid attention to the introduction at the start, you'll see I actually work in a strategy team rather than an innovation one. And an approach we often use in strategy is a simple 3-step model. Everybody loves a 3-step model on the screen. Where are we now? Where do we want to be? And how are we going to get there? So let's start off with where we are now. And actually, we're going to go back in time and begin with a little history lesson. So most of our large wastewater treatment works today are operated using something called the activated sludge process. And that was developed back in 1913 by Arden and Lockett. And it could arguably be considered the biggest improvement in public health in the 1900s. And it certainly also showed dramatic improvements in our waterways. Now, if you're not familiar with an activated sludge process, typically what that would look like in layout form is what's on the right of the screen there. The wastewater is initially held in something called a primary tank for a few hours, where most of the particulate matter settles to the bottom. And the water comes out the top and passes into aeration basins. And there it's mixed with a biomass or an activated sludge, bacteria that degrade the remaining organic matter. And the mixture is then settled again in a final tank, which separates the wastewater from the biomass. And the clean water passes out into the environment, and the sludge is collected and taken away for further treatment. And over 100 years on, we're actually still largely using the same process. So if we break down our asset base for wastewater at Scottish Water, we have a little over 1,800 wastewater treatment assets. And they're split across all kinds of populations. At the small end, we have the septic tank. And in number, that's actually the greatest number. And then we move up through primary, secondary, and tertiary treatments. And if we look at the breakdown again, where that goes, we've got a large number of trickling filters, and about 10% of our overall treatment asset base is activated sludge. So if that's only 10%, why am I making a big deal out of it? Well, activated sludge makes up the largest part of our population-based treatment. So if I move on to the next slide, this is a breakdown of every single treatment works in Scotland, so all 1,868 of them by population size. So right up at the biggest was Shield Hall in the top left corner. And actually all of these ones that you can see, and a large number of those across the top, these are all activated sludge treatment works. It's not until you get right into the tiny squares in the bottom right corner that we're looking at trickling filters and septic tanks. So by population, the activated sludge process makes up the largest part of our wastewater treatment systems. And one of the things we need to think about is whether it's time to revise that view. Now, for anyone who's based in Glasgow, and we were originally supposed to have this talk in Glasgow, let's bring this a little bit closer to home. So one of the largest treatment works in Glasgow, in Dalmarnock, that was constructed in 1894 originally, for all the fact fans out there. But this sewage works was upgraded in 1965, that's 55 years ago. And this slide's got some extracts on it from a fascinating paper I found, if you find this kind of stuff fascinating like I do. This was presented to the Institute of Municipal Engineers, which was an early participant of the Institute of Civil Engineers today. And this showed all the engineering requirements that were needed to convert Dalmarnock into this modern activated sludge works. And while this site has been further modernised since 1965, indeed it's seen the introduction of ammonia and phosphorus removal processes to meet tighter quality standards, the site itself still largely runs on this activated sludge process. And if you walk around the site, the layout really hasn't changed very much from this proposed layout drawing over 55 years ago. And there's a good reason for that. The activated sludge process is effective, it's reliable at removing the majority of organic pollutants in the wastewater. So why innovate? What might we want to change? Well, while the activated sludge process is very effective at removing pollutants, it does have its faults. The process is a huge energy consumer. I think it's been estimated that 3 to 4% of Scotland's energy production goes towards the treatment of wastewater. And additionally, the process creates volumes of excess biomass or sludge that has to be transported to another centre for further treatment, which adds to costs and emissions from the process. And finally, while we can tweak these processes to remove nutrients, it becomes more complicated to operate. And when we look at higher level pollutants, priority substances like pharmaceuticals, pesticides, and flame retardants, the process isn't terribly effective at removing those substances. So perhaps it's time to start thinking different from this process that served us so well for the last 100 or so years. So thinking forward to where we might want to be in the future. In Scotland, Scottish Water, we've recently published our strategic framework, and that sets out these 3 key ambitions for the future: delivering service excellence, moving beyond net zero emissions, and providing great value and financial sustainability. Now, each of these ambitions will overlap with each other, but there's also tensions between them within delivery. And without innovation, we won't be able to achieve them all. And underpinning these ambitions, there's a whole set of strategic objectives that will help us achieve the 3 ambitions. Now, I'm going to zoom in on just 3 of those that will be critical to transforming our wastewater service into SR21 and beyond. So firstly, enhancing the natural environment. We know that standard wastewater treatment has delivered huge improvement in our waterways over the last 100 years. But if we also want to look at improving our performance for things like those priority chemicals, and also look to improve the land and air environment as well, we'll need to think different. Similarly, we know the wastewater treatment process is currently a consumer of resource. It requires the use of electricity and chemical. And yet there is also resource contained within wastewater. So how might we go about harnessing this instead to fully embrace the circular economy? And finally, we need to transform our emissions. I imagine no one on this webinar is blind to the current climate emergency. And in September last year, Scottish Water announced its target to achieve net zero emissions by 2040, 5 years ahead of the Scottish Government target. And if we look at the current breakdown of our operational carbon footprint, we can see a large part of this actually comes from wastewater. Scottish Water's electrical demand makes up about 64% of its operational carbon footprint, and the largest part of this is taken up through wastewater process, including the pumping of wastewater, the treatment itself, and the treatment of sludge, or the bioresource byproduct. And another part of our operational carbon footprint that often gets forgotten about, I think, is that of the process emissions. So these are chemicals directly emitted from our wastewater processes, things like methane or nitrous oxide. And both of these chemicals have greenhouse emission factors many times worse than carbon dioxide. So addressing these and looking at how we reduce our process emissions will be a huge challenge and may require us to completely rethink how we treat our wastewater. Thinking a little more in the current frame of what we might need to do and what our drivers are for innovation is that of population growth. Now, across Scotland, our population is due to increase by about 5% in the next 25 years. And that's not a massive amount of population growth, but the countrywide figure masks some huge shifts in terms of regional shift of population within the country. We're seeing huge numbers be moving from the west of the country towards the east. Within Edinburgh, the Lothians and Aberdeenshire, we might expect to see growth in the region of 20% in the next 25 years. Now, we need to be sure that these growing communities receive effective sewerage services, but we also need to be able to do this without placing huge investment demand on our existing customers to build new assets. And achieving this will be a challenge. So historically, when we would been looking to address growth, if we'd had something like the activated sludge process, what we would do to address growth in a community might be just to create a parallel works, or even another one, doubling, tripling capacity. And we know that this does work, but it's also costly, both from an operational and a capital perspective, and land isn't always available. So some of our more immediate innovation projects have been looking at process intensification, so how we can do more with the assets that we've currently got. And this will help us to address growing populations with reduced need for investment and reduced carbon emission in construction. So there are a number of options out there for intensifying the wastewater treatment process that all look at different aspects of innovation. And these are just a few on the board that we've looked at in Scottish Water. So I'll take a couple of moments to look at a few of the trials that we've done in a little more detail. So first, let's look at the Narita process. This is quite an exciting one because it's one we've seen all the way from development stage up to a full-scale installation. And this is based on a traditional biomass type process. However, in this instance, through some clever bioengineering, all that bacteria is pulled together into a granule. And what that means is you've got a much higher concentration of biomass treating your wastewater. So you can treat more wastewater with a smaller asset to a higher standard. Now, because the process operates in a similar manner to something called a sequencing batch reactor, there's huge potential out there to retrofit this technology into wastewater treatment works that currently use that SBR type method. And that allows a significant increase in population that can be served without the need to construct any new assets. So Scottish Water first came across this technology and it was introduced to us maybe 7 or so years ago. And off the back of that and some promising work that came out of the Netherlands, we ran a couple of pilot reactors, one of which was in fact sited at Dalmarnock, the treatment works I mentioned earlier. And that's a picture of the pilot that we ran on an unusually sunny day over in Glasgow. And we put the reactors through a series of tests throughout that trialing period. So we tried, we had cold influent, we tried saline intrusion, we mocked up storm events. And the graph on the left shows the collated results from all of those pilot trials shown in that box and whisker plot. So the bulk of the results there, the upper and lower quartiles, are shown in the box, and the whiskers show the extremes of the results that we had come in. And what you can see was really largely a very successful trial. For the most part, the total phosphorus TP was well below an average of 1 milligram per litre, which was what we were looking for. Ammonia results, again, I think pretty much every result came in below 1 milligram per litre, which was really fantastic. And similarly, the BOD, the organic content of the wastewater, was well within our performance expectations, as was suspended solids. So off the back of what was quite a successful trial, we put forward a full-scale project. So next slide, yep, to be a photograph of our Narita installation at Inverurie. This is a small satellite town in Aberdeenshire that was both due to be upgraded with a significant capital maintenance project and also was experiencing quite a bit of growth in the catchment. So here we are in the final stages of construction for that site, and we're now at the end of commissioning. So quite exciting to see a process go from very early stages through innovation trials through to a full-scale installation. Now, the other pilot trial I wanted to briefly mention is at a slightly earlier stage in development is the microniche technology. And this is another sort of really exciting, really innovative piece of technology that we've been trialing down at our site in Bowness. So to try and summarize how it kind of works, you've got the little granules or biocatalyst, which is what the hand's holding on the left photo. I always think it looks like Rice Krispies, but it's actually little kind of beads. And they've got specific selected bacteria growing inside of them. And it's quite, I think it's really cool because you can select the bacteria that best degrades the wastewater, that are most effective at treating what you're after treating. Which is not what you typically get in activated sludge. You typically get the fastest growing bacteria that outcompetes everything else. With this, because the bacteria are embedded within the catalyst, you can select the most effective treatment, even if they're not the fastest growing biomass. And the picture on the right there is the pilot unit that we had down at Bowness. I'm going to see if I can show a little video of that in operation. Is that going to work? So that's what it looked like when it was up and running. Get rid of that. There we are. So really exciting trial, and we had 3 main phases. I won't talk you through all of the results, but that's the kind of the headline graph of what we did. Three main phases. So first was startup. And it took a little while for things to pick up. We certainly learnt a lot of lessons throughout the commissioning of the pilot trial for how you might increase the speed of that in the future. We then had a short period of what I've called normal operation. So just taking a standard influent in, running it through the treatment process and sampling the effluent, particularly with the ammonia and the soluble BOD, soluble organics in the wastewater. You can see that the effluent performance was really pretty good. So happy with that. We moved into phase 3, which I call testing the limits. So again, that's kind of pushing the technology as hard as we can. So how can we, if we increase the throughput or decrease the aeration, what if we mimic storm events, all that kind of stuff. So how well does the technology cope if you're putting it outside its typical bound of operation? And yeah, really quite happy with how that's performed. So hoping that will move through to the next phase trials and investigate options for full-scale treatment. The other aspect of microbi that's been really, really interesting is looking at suspended solid production. So one of the big claims of the technology is that they don't produce a biomass or any excess biomass because all the bacteria are embedded within the catalyst. We wouldn't have any secondary surplus sludge that we'd need to collect and then take off site and treat. And you can see the results there in terms of the suspended solids. Actually, for the large part, what was coming in equals what was coming out. So we weren't generating any excess biomass. You know, it also meant that maybe we weren't degrading any of the suspended solids coming in either. So there's pros and cons to that result. But on the whole, we could pretty much confirm that we weren't generating any excess biomass. Now, I couldn't talk about our microbi trial at Bo'ness without doing a little plug for the Innovation Test Centre down there. So the Bo'ness Test Centre, it's a live wastewater treatment centre with a dedicated test centre attached. So halfway between Edinburgh and Stirling. And that hall you can see in the photo contains feeds from the main wastewater treatment work of raw sewage, settled sewage and final effluent from the treatment works. So it allows companies to come in and demonstrate pilot scale reactor technologies. And these facilities, and there's a complementary one out there for clean water up in Gorthwick as well. These facilities are run as part of our commercial arm, and therefore they're available to anyone who wants to test the technology there. So it doesn't have to be a Scottish Water trialling the technology, although we certainly do trial a number of things down there. We've had other businesses in to demonstrate their own products and processes. And we've also collaborated with university research teams as well to help them with various projects. And there's an email address there if that's of interest to anyone to get in touch with them. So if that's some of our more immediate innovation, how are we thinking more about the long term? So going back to our strategic framework and what we might need to do to achieve our 3 strategic ambitions. So our innovation team have been developing a series of route maps and challenges for innovating, which are designed to align with our strategic framework and help set the direction for innovation. And I should say that these challenges for innovating are still in our draft phase, so we haven't published these yet. But the hope is that by going out there and setting out what our challenges are, we can invite businesses and researchers to help us answer the questions we want, rather than what sometimes happens is folks come to us with, I've seen some really cool innovations that, exciting developments in technology, but if they don't suit our needs as a business, we're unable to take them forward and it doesn't help us move towards our strategic direction. So by going out there and setting our challenges for innovating, we're hoping that the industry and the supply chain will help us take up this challenge and come up with new ideas. And from the back of that, we're hoping to develop 4 demonstrator projects. And the idea of these is to prove at-scale versions of these step change innovations that we're after. Now, the projects shown here cover all aspects of our strategic ambitions. But the one I particularly want to focus on in the final part of this presentation is talking about energy and resource factories. So if we're to move into this world where we've transformed our emissions and enhanced our natural environment and fully embraced the circular economy, then we're going to need to rethink our attitude to wastewater. And we're going to need to move away from thinking about wastewater treatment works and towards thinking about sewage as a potential source of resource and energy for the future. So we know, for example, that wastewater contains far more potential energy than is currently used to treat it. And if you remember the emissions footprint slide from the beginning, quite a large portion of that energy that we're currently using to treat, we ought to be extracting, we ought to be trying to harness that from our wastewater itself rather than bring it in. Now, this flow sheet that I've put up is a little bit old now. It stems from some work we did with Cranfield University a few years back. But I think it's still very relevant today. And this is looking at what potential options might be out there for wastewater treatment works for the future. What might that look like? So I just want to focus in on a couple of aspects of this flow sheet that I think are really exciting, and the kind of technologies and the things we might be looking for innovations in the not so distant future. So starting off, the main treatment in this particular flowchart, and there are a few, was using an anaerobic membrane reactor. So the key bit there is the anaerobic part of the reactor. We know that at the moment we blow oxygen, and we spend all this energy blowing oxygen into our wastewater to try and treat it. But actually, if we're able to do that anaerobically, so without blowing air into it, not only are we not requiring all that energy to blow air around, but we can also generate methane, which we're able to harvest and then use as a potential bioresource. Now, I mentioned earlier about process emissions, and methane certainly is one of those. So that is something we need to be cognizant of and careful that if we are deliberately generating methane, that we are capturing it and then using it, and that we're not letting it be emitted out to the atmosphere. And another big advantage of anaerobic technology is that it doesn't produce nearly as much sludge as an aerobic one. So again, that's less excess waste being generated that we would need to tanker around. Now, the next part in this flow sheet is something that's really quite different to the way we treat wastewater today. But one of the, call it, side benefits of anaerobic treatment is that it only deals with the organic fraction of the wastewater. So it doesn't remove nutrients like ammonia and phosphorus. So this actually gives us a really great opportunity to directly recover these resources and potentially use them. Ammonia and phosphorus, both key aspects in fertilizer, amongst other things. So one of the treatments that we've looked at is an ion exchange method. And that's really interesting, and it's really different because it doesn't use any form of bacterial process, which is what we often do at the moment. And why that's interesting, a byproduct of ammonia treatment, doing that biologically, is this nitrous oxide byproduct, only emitted in small amounts, but as a process emission, it's really, really potent. It's 298 times more potent than carbon dioxide if emitted to the atmosphere. So if we're able to treat and remove ammonia abiotically without this biological process, not only are we potentially harvesting that ammonia so that we can use it, but also we're mitigating against this nitrous oxide byproduct. And then finally, of course, we will still produce some sludge, some bioresource from the primary stage of the treatment. And we need to understand how we can best generate energy from this, as well as looking at potentially useful byproducts like struvite, ammonia, or perhaps even higher value organic chemicals. There's so many potential resources in our wastewater that there's potential out there to harvest. So that's just one of the potential routes for that demonstrator for an energy and resource recovery factory. And I really think this is something that we need to focus on for innovation to help us move into the future and to help us achieve those strategic objectives. And I'll just finish up with the one final thought. I've rambled on a lot about wastewater treatment technology and how the activated sludge process has had its day and all the alternative options out there that we might want to employ in the future. And if that's a picture of Dalmarnock 55 years ago and thinking about what it might look like 55 years into the future, and I hope that Dalmarnock isn't still employing the same activated sludge process, but we also know that the carbon costs involved in construction are huge. So my hope is actually that it might look fairly similar, that we're able to reuse existing assets and materials. So perhaps the layout will be quite similar, but what's inside all of those concrete boxes and how that's all working might be very, very different. So I hope that's given you a brief flavour of innovation at Scottish Water and the kind of things we may be looking to into our next regulatory period, SR21 and beyond. So thanks very much. And I think, Finley, I'm handing over to you to help with some questions. Oh, are you there, Finley?
Oh, can you hear me now?
Yes, loud and clear.
There we are. Thanks very much for that presentation. That was fantastic. So one of the questions, sorry, that we've had so far relates to the Narita process, and what it is how does this process compare with an equivalent activated sludge plant?
Yeah, really great question. Something we need to consider. Of course, any new asset that we build needs to deliver value for customers. So straight out of the box, in terms of capital cost, probably Narita would be more expensive. You know, obviously every project is unique. So it may be more expensive in terms of a capital cost. The way we look at things in Scottish Water, and I think most of the UK industry is going down a kind of whole life cost TOTEX scenario. And that's where Narita starts to come into its own. Because of the level of process control on the technology, you're able to make savings in terms of your energy demand, and also through the nutrient removal. You get much reduced chemical demand. So yes, there may be a capital cost up front, but at least for the Inverurie project, when we compared the whole life cost, it ended up being the best solution for us.
Excellent. And another one that's come in there is what is the process used at Scottish Water to decide which technologies to trial?
How do we decide what technologies to trial? Well, partly it's what we become aware of. It's what's out there, what's already been trialed. So what can we learn from trials that have already happened? Do we already know enough from what's been trialed out there to give us confidence in the technology? But if maybe there's not enough knowledge, but there's something that really does look promising, so how will it help us achieve those objectives? So what's the problem we're trying to solve? So looking for things like process intensification. So how can we do more with what we've got? How can we improve our effluent consent? If there's things that meet specific needs that we have, but there isn't enough information out there, but that look really promising, that's the kind of things that we've looked more towards trialing.
Excellent. As one question that I had myself actually was, what do you consider to be the biggest sort of constraint to innovation in this regard? Does it tend to be economic factors, or is it space, or achieving environmental discharge standards, or possibly some other factors?
Yeah, so many barriers to innovation, and I know there's plenty of SMEs out there that would probably have a much better answer to this question than I would. I think the water industry, as perhaps any heavily regulated industry, is quite nervous about change. And so I think, yeah, it's something we need to work closely with our regulators with to help us overcome those barriers. So improving our relationships in Scotland with SEPA and looking at how we better trial innovation is something that could probably help us.
Cool. Okay, and I think we've got another one that's just come in here as well. What is the latest thinking in overcoming the issues associated with low temperature, slow reaction rate and high CH4 solubility in effluent for anaerobic processes?
Gosh, well, that's an hour's seminar in its own right, I think. So there's certainly technology out there, and there's been demonstrated in a number of papers that anaerobic treatment is effective at low temperatures. Obviously, the reaction kinetics are lower, so there are trade-offs to be had at low temperature. In terms of high solubility, there's been some really interesting developments in terms of how you remove dissolved methane. So looking at various membrane technologies and other solutions for that. So there's an awful lot of stuff out there, and I'm conscious of not waffling on for too long. But yeah, feel free to follow up.
Perfect. And another one that's come in there is that one of the attendees is aware that the Arvia has a trial plant with Scottish Water, and it's combined with ion exchange technology that you mentioned. Do you know if that's on the drinking water side or if it's on the wastewater side?
Gosh, so I've not heard of the Arvia plant, so that would suggest to me it's on the water side because I'm a wastewater nerd. So I know we have been trialing some ion exchange technologies on the water side. I don't know the commercial names of the individual technologies. So yes, I would imagine that it would be on that side. How long does it take to get from lab bench to commercial scale? Well, I think the typical figure is 25 years. But yeah, it will vary from process to process.
Wow, it's quite a long time to get that process kind of through all of that, isn't it?
Mm-hmm.
So with regards to the impact of increased storm flows and catchments and into the works, what innovations are you looking at to reduce storm flows and reduce the need to build large storm tanks?
Yeah, so our policy on surface water is no more in, what's in, out. So trying to get rid of stormwater from our network. You know, in an ideal world, we would all live on a separated sewerage system, but that isn't the system we've inherited. So with new developments, we look for things like suds ponds, and so surface water is not put into the sewerage network, so there shouldn't be storm inflows. With existing infrastructure, it is much harder, and certainly my colleagues on the network side do a lot of work into trying to improve that.
Perfect. And do you know, is there sharing of knowledge between different UK water companies on what technologies work on what sort of sites?
Certainly, yes. So there's a number of knowledge sharing groups out there between the different water companies where we're able to share our experiences of technologies and any of the challenges that we have. So yes, we do all talk to each other.
Excellent. And how well do the new technologies handle changes in feed? For example, the current lockdown has led to a reduction of trade effluent, so potentially weaker or higher flow volumes.
Gosh, yeah, okay, so a couple of bits piled up in there. So new technologies, that's one of the things that is quite important when we're testing a new technology is how it was going to handle different scenarios. So we talked about low temperature, storm flows, you know, we have climate change, we've got longer, drier summers up in Scotland now, so we do see stronger influence. So that is something that we do test. Current lockdown, it's been really interesting actually. So different treatment works have experienced this in different ways. So you may have seen in the news about there being less demand for milk production. So there's been a couple of treatment works that have seen huge amounts of milk being discharged to the sewer, which presents challenges. Satellite commuter towns, so normally you'd expect maybe a high load come in the morning and then everybody goes off to work, to school, and then comes home again, you get your loads in the evening. Actually, some of those satellite towns are having to deal with much higher concentrated loads throughout the day. And that's really where we've seen big changes throughout lockdown.
Okay, and what do you think about tackling microplastics and microfibers in wastewater and sewage sludge? Do you think the innovations that you've mentioned might help that?
Yeah, the million-dollar question, microplastics and microfibers. I think there's still a lot of more research required in that space. So I think the specific ones I mentioned, they're not designed specifically to deal with microplastics, microfibers, but it's something that we're constantly aware of. And actually one of our big challenges is how do we just get them out of sewage in the first place? So we know that the further down the treatment train you go, the harder it is to reduce these things. So actually if we can do customer education and help stopping microplastics or priority chemicals as well getting into the sewer in the first place, that's really where I think the big wins are to be had.
Excellent. And how long do you how long till you build
I'm reading the question. I don't think I can comment on competitors. So it's we're still evaluating the microbial technology, looking to compare it against a few other different treatment technologies for some of the growth projects that we've got coming up. So certainly it's in contention. But as we've said, and with Narita as well, it needs to stack up on a whole life cost scenario. So it needs to be cost competitive as well as being an effective technology. We can't just put in new technologies because Rachel thinks they're cool, unfortunately.
Excellent. So unless anyone's got any final questions, we can wrap that one up there. So I think that probably concludes the question and answer session. So I think on behalf of CIWEM and the Scottish Branch Committee, I'd just like to thank Rachel very much for delivering this fantastic talk. It's been great to hear about the wastewater innovation at Scottish Water and kind of what you've got planned for the future. I'd also like to take a couple of minutes to thank those who've joined us this evening for the webinar. And if you've got any questions about CIWEM itself, or if you'd like to get involved with the committee, please get in touch with our chairman, Alice, who opened the presentation earlier on. Additionally, I think if anyone has any other burning questions as well, feel free to get in touch with Rachel, who's very kindly offered to answer any further questions following her presentation. So yeah, once again, thanks very much for listening this evening.
Great, thanks Finley, thanks everyone.